Hi, thanks to everyone for coming for this lecture. It's going to be great. Let me introduce Professor Valerio Lucarini. He's from the University of Leicestershire in England. Before that, he was at Reading, also in England, and Hamburg in Germany, and then Bologna in Italy. So he's traveling and he's headed to the right place, I think. uh, and he, I'm very bad at doing these kind of introductions, but some of the notable things that he has done is that he did the H.G.U. Lorentz lecture, which is the designated honor for the nonlinear geophysics group. And he also got the Society of Industrial and Applied Mathematics the Earth Prize that they give. So he's been recognized for these things. I followed his work for about a decade at least. And some of you may have met Davide Farinata, who gave a talk here last year. Well, Davide was his PhD student. So there's a lot of commonality here. Now about the talk itself. Uh, the climate community sort of has sorted itself into two and a half groups. One is a group of people who call themselves modelers, and I call them model runners because they're not actually developing new models. They go and run a scenario and then tell the world about it. Uh, the other group is the climate dynamics theory group. And the half that I was talking about are the people who, within that group, are adept at looking at the fluid mechanics aspect or the thermodynamics aspects of the theory, as well as the stochastic dynamics aspect of the theory and the nonlinear dynamics of the theory. So Valerio covers that 1.5. And so that resonates much more with me than the model runner people. So I'm very happy to have him here and talk to us about some of the dynamical attributes and actually how to think about the data and interpret the data as well, specifically in the context of extremes. And this is one of the areas within the Water Institute and SCAS that we are trying to build up. So Valerio, we are very pleased to have you here.
Yes, no, you
have a mic, right?
Yeah. Thank you. Okay.
Oh, I've been told to tell people that there is actually food there, but please stay away from the food until Valerio.
Yes, like so. I know you've come for the food, which makes sense. So I try to make the wait for the food as pleasant as possible. So it's great to be here today. I work in different areas of, let's say, the interface between maths, physics, and climate science, including work on tipping points, on climate response, reduced order modeling, and extreme events. So today I'll try to give you the perspective on persistent extreme events in the atmosphere, in particular having in mind heat waves and cold spells. So I'll try to provide a statistical angle on the problem, but I will also try to provide you a dynamical angle on the problem. So can we sort of make a sense of the special features associated with the persistent extremes? And can we understand how special the dynamical conditions, dynamical aspects leading to them are? Okay, we will need to use different tools. So it's not a top-down work. It's something that fits under the umbrella of complexity. We need to take evidence and ideas from different angles, use different pieces of mathematical techniques, numerical modeling techniques, ideas in statistical physics, as well as our intuition, okay? So I try to convince you this is fun. So the big questions I want to tackle is it possible to introduce a notion of typicality for extreme heat waves and cold spells? So I want to convince you at the end of the day that we shouldn't use notions like black swans to understand such events. These are not crazy flukes of the atmosphere, but there is something fundamental. But we need to distill the information to find it. And is there something special about the dynamical processes leading to that? Of course, the equations of motions are always the same, but is there something special? Remember, we have to consider that in complex systems, often the dynamical properties, and in particular the instability, can be extremely heterogeneous. So mathematically speaking, we have to go beyond our intuition of so-called hyperbolic systems, okay? So there is also a technical mathematical aspect we will touch that I think is very relevant for the problem of predictability. And in which sense the dynamical causes of extreme events, which are the so-called atmospheric blockings, are true modes of variability of the atmosphere. Okay, we start. So I am a physicist by training, so I like to give a sort of a broad physical framework. So when we talk about the climate, we talk about a non-equilibrium system. So equilibrium is a bad word with climate, because equilibrium, just like in life, equilibrium is death. Equilibrium means there is nothing happening. So the climate is a strongly driven, forced and dissipative system where the non-equilibrium conditions are due to the fact that the solar radiation is absorbed heterogeneously. In particular, is absorbed preferentially at low latitudes rather than high latitudes, Phoenix more than Hamburg, and at low altitudes rather than high altitudes. So the surface is warmed up. Okay? So the entirety of motion, so the geophysical fluids, the entirety of phase changes and transport and so on, is a desperate attempt of this complex system to establish what, in the language of people like Joe Lebowitz, would be called a non-equilibrium steady state. And this is a process that goes on. So non-equilibrium steady state conditions are maintained by the non-equilibrium forcing. And if we look at the phenomenology of the climate system, the climate is a multi-scale system. So that means it has variability on a broad range of scales. I like to say that it is a universe in itself. So we have 15 orders of magnitude in the temporal and in fact also in the spatial variability we see in the climate. This is the so-called Mitchell diagram. This intuition comes already from the 70s. Now, what we learn today, if we want to connect also to modeling, the different regions of the climatic spectrum are dominated by different subcomponents of climate. Still, there is overlap everywhere. So we need coupled processes. And there is no spectral cutoff. That is, it's very hard to use asymptotic theories to find effective equations. So this is instead has been a massive success in many areas of applied maths, as an example when we study material. Remember, since the system is multi-scale, that strictly speaking, there is no reference state. And strictly speaking, the climate has always changed and will always change. That's a separate matter from saying that it's not possible to attribute the ongoing climate change to anthropogenic activity. It is possible, but we need some very special statistical techniques. And the development of these statistical techniques is the main reason why Klaus Hasselmann received the Nobel Prize in Physics. And we can work on these techniques and improve them, in fact. So now, today, we focus on the atmosphere and we look at a range of temporal and spatial scales, which are indicated in the red box approximately. So we're going to talk about the synoptic activities, so thousands of kilometers up to planetary scale things, tens of thousands of kilometers from days to months, roughly speaking. So this is the domain of the synoptic up to so-called low frequency variability of the mid-latitudes. Now, what is, thermodynamics was mentioned. A genius concept that was proposed by Ed Lorenz well before his famous paper, non-periodic deterministic flows, is the notion of the energy cycle, which quantifies the maintenance of non-equilibrium in the atmosphere. In the atmosphere, available potential energy is continuously replenished by the non-equilibrium condition. It's transformed into kinetic energy, and this kinetic energy is then decays because of friction, basically. So this is the essential ingredient of the general circulation of the atmosphere, and it can be treated formally as an engine. So the atmosphere is an engine in the sense of an actual engine, a thermal machine that can be studied using the methods of classical thermodynamics. Now, again, we focus on the atmosphere now. So from the climate, we reduce our scope to the atmosphere, to the mid-latitudes, to a range of frequency, as I said, between a few days and, let's say, 1 month or a few months. And we are able to do a spectral analysis of the atmospheric dynamics. So these are tools, Hayashi spectra introduced in the 70s. And as an example, you can separate from the spatial temporal variability of the atmosphere into westward propagating waves, standing waves, and eastward propagating waves. Sorry, standing waves, eastward propagating and westward propagating. And you see here, so this is omega, this is k. The omega, the k, is larger than 0. That means you have group velocity going towards west. So these are the synoptic variability. And now you see that this spectral characterization is fundamentally different from those of the low frequency standing and eastward propagating. So there is a qualitative kinematic difference in different components of the atmosphere. And in particular, the westward propagating, the eastward propagating disturbances are basically associated to mid-latitude cyclones. And again, we are far from the tropics. And on very large scale, we have the so-called teleconnection, like the North Atlantic Oscillation, that is at the very extreme of this range of frequency. And on the standing waves, what is, this is a spectral analysis. So remember, you can look at the problem from a spectral viewpoint or from the angle of space-time. So if we live in space-time. Remember, not everything lives in space-time. Optics lives in frequency, okay? For optics, the real world is frequency. For us, the real world is time and location. So now, an important manifestation of the low frequency variability of the atmosphere are the so-called atmospheric blocking. So these are long-lived deviations of the flow from the usual jet. And these are simply the most studied problem in dynamical meteorology since the beginning of dynamical meteorology. So people are studying this intensely since the 50s until now, because this is a non-solved problem, okay? Why? And I will specify what it means. So you see that the flow is deformed up to the point that the topology of the isolines of pressure is different as opposed to the usual conditions. The flow is blocked, comes back, and persists in this kind of qualitatively different conditions for a number of days that can range for, say, a few days up to months. And now we get at the same time persistence and stationarity, especially. So this means you're going to build up anomalies. So if you are in this part, you're going to get an excess of flow from the south, so you're going to get warm conditions, and here you're going to get cold conditions. You might get rain or drought. So immediately you see this leads to persistent extreme events. Now, these blockings occur more typically either in the Atlantic sector or in the Pacific sector, or sometimes in both sectors at the same time. This is called the simultaneous or global blocking. So this is, since the 50s, this is much studied. Okay, and this has led historically to the creation of the so-called weather types. You see all tables in all books and all journals of meteorology where people try to do this kind of classification and infer qualitative features of the weather, just like I'm doing now. So this is, if you want, super classic. Okay, I'll try to go from this to something that takes into account more modern quantitative methods. So we need to understand these things. And why we need to understand these things? Because as an example, omega blocks, which takes the name from the shape of the isolines, are responsible disproportionately for extreme events. So this is a textbook case of the 2010 heat wave in Russia, one of the most devastating persistent heat wave that has hit Eurasia in the last decades, which has led to many deaths, huge damages. And that's something that's very interesting, is that it has led to what is called the cascade effect. That is, while there was this huge anomaly of high pressure in Russia, downstream something happened. So at the same time of the really extreme heat wave in the European part of Russia, you get torrential rains in Pakistan, leading to some of the most devastating floods in human memory. 20 million people were refugees as a result, were evacuated as a result of these floods. By the way, the record was beaten last year by another event of this sort, okay? So now, we have that these anomalies can impact. So the dynamical cause is the same for these two apparently separate events. So we want to understand on one side the properties of this heat wave as a heat temperature anomaly. On the other side, we need to understand what's special about these blockings. Okay, So I will, in my presentation, I will do a bit of both. Some dynamics, some statistics, and I'll try to, it's a bit of, not a disorganized, but I want to give you some ideas coming in parallel, and you will make in your mind the story you prefer. It's a series of suggestions, okay, rather than trying to be totally top down. Okay, so now let's go to the glorious time of dynamical meteorology. We go to the 80s. Some giants of dynamical meteorology are mentioned here. People try to understand blockings through classical theory. So they take the equation of barotropic or baroclinic vorticity model, and they try to find multi-stability in the solution. So we know that one solution will look like zonal flow. We want to see under which conditions we get a second competing solution that looks like a block flow. And the idea is, this is the deterministic case, then I add some noise into my system due to higher frequency disturbances, and then I get magically the system to jump from one state to the other and back and forth, which is what I observe phenomenologically. This is the same time of works like stochastic restaurants, huge emphasis on metastability. So it's the same scientific environment and flavor. Another point, totally different viewpoint on blocking, comes from the school of Brian Hoskins from Reading, who instead studies the problem of persistence from the angle of conservation of potential vorticity. So this is instead a fluid dynamical angle. So we have a dynamical system angle and a fluid dynamical angle. Of course, none of them is right, and neither is right, neither is wrong. Both are useful, okay? So why we want to study these blockings? Because the blockings are a formidable barrier for medium range prediction. There is an entire institute, the ECNWF in Reading, that focuses on medium range prediction. The problem is not predicting the weather in a few days lead time, but predicted beyond 10 days, 2 weeks. Our ability to improve this, the prediction of this range is limited, has improved slowly in time. If you want, it's a logarithmic improvement, given that we have an exponential growth in computing facilities. Things might be getting a bit better now with some AI tools, but as a matter of fact, blocking reduces dramatically our predictability. Why? Because it's very hard to forecast the onset and decay of the blocking. Once we have the blocking, it's going to be either basically sunny or cloudy, but we don't know when it's going to start and when it's going to end. So this makes things very hard. Okay, and there is else that even climate model have a huge difficulty in predicting the statistical properties of blocking. So one thing is the forecast, and another thing is the statistics. So we take super sophisticated climate models that do a great job in simulating some of the key properties of the climate system, that do valuable climate change prediction, but they are always an Achilles heel. That is the statistics of these things. Unfortunately, these things are very important. So this is a barrier for our ability to assess climate risk and how this climate risk changes as a result of climate change. Okay. Now, as I said, these blockings, so we have a problem in the modeling in representing this model, in these features, these blockings, and the impact, as I said, is especially serious about climate risk. So let's go to the summer of 2003. I was in Finland at the time, and it was beautiful. I was in the forest and finishing my PhD thesis and picking up mushrooms and all these things. My girlfriend was in Italy at the time, and she was getting crazy of the very hot temperature in Florence. She had almost hallucinations, and it was even worse, in fact, for my friends who were living in France. France had the most devastating heat wave ever, which led apparently to about 50,000 excess deaths. So an entire epidemiology was done on this. Basically, by the way, kind of epidemiology that was then repeated during COVID, okay, to evaluate the excess deaths due to an event. And what they found is this graph, which is very interesting. This is more or less the onset. On the left, you have the onset of the heat wave, and the graph, the histogram are the excess daily deaths. What you see is that when the heat wave kicks in, there is a positive anomaly in the number of excess deaths, but not that. The number of excess deaths is not proportional to the temperature anomaly, so there is a threshold effect, but grows with time. Why? Because it's the accumulated heat that kills you. Okay, so note, the daily number of deaths grows more or less linearly with time. That means that the accumulated number of deaths grows quadratically with time. So a heat wave lasting a month, it's much, much more devastating than 2 heat waves lasting 15 days. Okay? So persistence is key here. So we can't just summarize the event as one number. It's at least 2 numbers: threshold, like intensity, and persistent. And persistent is as important as the threshold. So we want to understand put together this puzzle. Of course, I have not succeeded at all in putting together this puzzle, but I worked hard to try to do that. So I'll show you these 2 slides, what has been the science flow for me on this research line for me. So we started by looking at the statistics of this object. We tried with my PhD student Shuba to understand the dynamical features of blocking events, why they are special, and then went from a local analysis in local Lyapunov analysis to a global analysis done using unstable periodic orbits. So we try to use some different tools of dynamical system theory to understand the properties of blockings. And then we came to the conclusion that indeed, yes, blockings are dynamical oddballs, something strange, but still something we can characterize, both statistically and dynamically. This is PhD of my student Chiara Maiocchi, and then statistically using a Markov state modeling, basically, so statistical mechanics. And the other thing, as related work, is on the heat waves of cold spells. So how do we treat extreme events? Can we characterize the dynamics of these extreme events? And here, what has been very important has been mostly the use of large deviation theory. So large deviation theory finding asymptotic laws of universal value. So we push us to the extreme, and somehow pushing us to the extreme allow us to extract fundamental properties. Okay? And more recently, with some colleagues from Australia, we used another data mining technique called archetypal analysis to extract the global patterns associated with extreme events. So now, let's see. It's not moving forward. It's going backwards. Okay, so now, what is this large deviation law? So large deviation law is, let's say, the foundation of modern statistical mechanics, and tries, in its simplest form, to study limit laws for averages. Okay, I have a time series, you can think it practically, and I study the limiting distribution of blocks, of averages over blocks of length n of my variable of interest. One could say, who cares? Okay, fair enough. But I'm interested in persistence. So in this case, it works. So now, under very general conditions, and there is an entire branch of mathematics coming out of this, I will not discuss this. You have that if you take sufficiently long n, the probability of this average having a certain values can be written as an exponential law of this kind, where n factors out, and then there is a function which is only a function of the basically x of the value where I'm aiming at. And this is called the rate function I of a. Why is this relevant? Because it tells you that if n becomes large, all this probability is concentrates, and concentration will be a keyword, near the minimum of this rate function, because all the rest will decay exponentially faster with n. So a special case of this is the law of large numbers, or the central limit theorem. I mean, things should be made more formal, but just to give you a sense. So this is the generalization of the central limit theorem to large deviation. That's exactly what it is. Now, very important, why is this useful? Because if I'm able to establish somehow that I have converged in my estimating the large deviation law for a certain n star, I have predictive capability to study the return times of events that have a persistence longer than the one I have studied. So I have fitted a universal model, okay? So I don't need, so I study persistencies up to a certain number of days. I'm able to predict the probability of return of events of the same amplitude or different amplitude that last a longer number of days. So it helps me to estimate return times, not in an empirical fashion, because I have converged to a law. Okay? That's why it's useful in principle. So of course I don't know if this is going to work. I have to test whether this is going to work. So with Melinda Galfrey, then PhD student, and she got for this kind of work the Turcotte Award for Best PhD in Nonlinear Geophysics in 2019. She used a simple model of the atmosphere, a simple primitive equation model, and we tested this hypothesis. How well does large deviation law predict return times for large, long-lived fluctuations of the temperature on the surface of this atmospheric model? So it's a very simple, this is really a fluid dynamical model, and somehow the result was that, yes, it predicts extremely well return times up to for very persistent heat waves. So these are heat waves in this model. We find, let's say, it performs even better than extreme value theory for corresponding observables. Somehow we are digging into the fundamental dynamical properties of the system by exploring these special extreme events. So step one, yes, these things work, okay? But this is a very simple model with all the symmetries. So then we decided, since we were in Hamburg at the time and we have a close proximity to some of the leading modeling center from Max Planck Institute, we decided to try to test this approach with data coming out of a, let's say, state-of-the-art IPCC climate model. Can we study heat waves in a real model with these, equations? Okay, is this going to converge? So, and we chose some regions that were historically used for studying climate change and climate variability, the so-called climatic hotspots. These were a big piece of climate literature in the early 2000s. So we took these regions and tried to study persistent temperature anomalies using large deviation theory, both locally and both in spatial averages. Okay, so it's the climatology of extremes. Now, miraculously, to my greatest surprise, we got convergence. So somehow we found that, yes, you can define this rate function. So yes, the climate dynamics, despite the, all the complexity of the modeling, this is a model with order 10 to the 7 degrees of freedom. So it's another class. Yes, you get large deviation laws. So somehow mathematics wins, okay? Okay, this is good. Why? Because I am able to estimate, so even if my model gives me only a certain range, I have ways to extrapolate in a way that is controllable. And second, I learned that climate change, by comparing different climate models, the way climate change impacts this. In particular, we see that climate change not only, of course, shifts the average to higher value, but changes the shape of the rate function. In particular, it makes large fluctuations easier to occur. Why? Because it dries the soil. So you lose thermal inertia. So now we see a physical interpretation of the change in these mathematical properties. It starts to become interesting. And instead, if we look at in the winter, we get that the rate functions become steeper. Why? Because as a result of climate change, we know the meridional temperature gradient is reduced, so baroclinic activity is reduced, and so waves are less intense. So, okay, starts to become interesting. Okay, there is a merit in this. And then, we have a climatology in this model, of course, of this. So let's say the tools seem to be working fine. And playing a bit, you are able to estimate the relative probability of events of different duration and different intensity. So there is a predictive power in terms of probability. So by using this mathematical tool, I learned how to estimate probability of unobserved systems. But still, this is a sort of a classification. So it's a climatology in the old sense of heat waves, which is fair enough. We have proposed, as Melinda, in fact, has created a new method to do a climatology of extreme waves that is not, remember, we are not targeting the tails. Here the tails become the center of attention. So it's very different. We tailor the theory to the tails, not to the bulk and then extrapolate. Okay, it's a very different angle. But there was something that we really wanted to understand. Can we characterize these events? Is there something special about these heat waves? Are they just, random but big fluctuations like the others, or is there something special? So then I came across beautiful papers, two beautiful papers by De Matteis, Grafke, van den Eyden, in total it's three, where they were studying the problem of freak waves, hydrodynamic freak waves, which, as you know, is a major risk in maritime industry and in coastal protection. And this has been studied for many years using, as an example, nonlinear Schrödinger equation and many other things. They changed, using a statistical mechanical angle, the approach. Instead of trying to understand how you get a freak wave, we know there are freak waves, they reverse the argument. Assuming there's been a freak wave, how do I get there? So if you want, it's a Bayesian approach. And what they proved, actually quite rigorously, is that under very general condition, you get that the more you consider extreme freak waves, the higher is the target, the more well-defined is the set of initial conditions and the path leading from this initial condition to this final target. So instead of trying to get the right direction, you go backward, basically. Okay, and there is a most likely set of initial conditions and a most likely trajectory that leads to that. They verified this numerically and experimentally on a water tank. A beautiful piece of scientific work. So our bet was, okay, let's explain you how this works. Okay, in qualitative terms. Assume you are in Phoenix and you are in a room together with 4 people that are at least 7 foot tall. Where are you? Of course, you could be anywhere in this room, but I don't think there is anyone. So most likely, if I have to bet, you are watching an NBA game and the 4 people are the 4 centers. I even know who they are if I watch the program. Okay? So you go from, by imposing this condition, so it's a condition, one condition, I go from an infinite dimensional phase space, I reduce myself to a very, very low set of cases. This is the same idea. Not that it's delicate, because if instead of 7 foot tall, I say 6 foot tall, this room is enough. Not me. For me, 6 foot tall is very tall. Okay? But if I go 8 foot tall, there's nobody ever been, probably, if not in the mythology of giants. So you see, I have to push things high, but not too high, otherwise I lose any event. Of course, it's possible for human genetics that this will happen if we repeat the word many times, okay? So the typicality emerges as I push my threshold high, but not too high. Not beyond the last event. I need to keep some statistics. Okay. So now the bet was, can we do this to study atmospheric heat waves and cold spells? Of course, these are infinitely more complex than the freak wave, but the idea is the same. So we started initially these 3 events, 2010 heat wave that I mentioned before, this much less studied and phenomenally interesting phenomena, the Mongolian soot. This is very long cold spells that impact quite regularly the central Siberia. These are responsible for basically, huge impacts on nomadic populations. These have been drivers of migration in the past from Mongolia towards China, Mongolia towards the West, and so on. So that's why Attila it's known why Attila went to the West, and we Westerners say the barbarians invaded us. Okay, these were Huns, a population that was escaping from death, white death, if you want, due to this. And same with the Tamerlan later, and same with many invasions of the Chinese Empire. This is actually the reason. It's documented thanks to the chronicles of the Chinese Empire. And as an example, the 2019 cold wave in America, and probably this one now as well, I'm most sure. So is there something, can we interpret this event using this apple? Okay. What we did is we took the same model, runs I showed you before, the one we used for the climatology, and we tried to select in these 1,000 years all the events that had an anomaly of at least 4.5 degrees lasting for 30 days. This is the observed 2010 event in Moscow for this climate run. And then we see how many these events there are. And then we look at the fields averaged over all the events and for each individual event. And what you discover is that these events look very similar to each other and look very similar to the actual 2010 event. Of course, they're not identical, but statistically they cluster together. So somehow you find a class of events that are, Russian heat wave-like. And this can be made statistically robust. Okay? And then these are the 20 pseudo-Russian heat wave obtained by the model. So I put one constraint over 10 to the 7-dimensional model run for 1,000 years. And I classified this. You see, this is the scale. It's, 1/4 of the planet almost. And they are much more similar to each other than from any random event chosen in the same period. Not only, if you push your threshold up in terms of intensity and duration, the clustering becomes better and better. So you are really following what in statistical mechanics is called the concentration properties. You are pushing this event and you are finding their commonality, because there are only few ways to construct such a heat wave, whereas there are many ways to do an average heat wave. Okay, so this is the idea, without going into technicalities. And this was a second confirmation that now if you take these events of the model and you look at the precipitation, you discover, which has nothing to do with our way of selecting the events, you get an anomaly of precipitation exactly in the northwest of South Asia, where you had the precipitation in 2010. This anomaly. So you are really capturing some strange large-scale connection of the atmospheric flow. Okay, so there is something deep in these events. And if you repeat it for the Mongolian zone, the result is even better, because this is just to give you a sense of the anomaly. 10 degrees anomaly lasting 30 days. Okay, so with temperature dropping to -40 or so on. So this is a huge event. Look at the scale. It's the entire Eurasia, basically. And I can tell you, and you will see actually in the next slide, in this case, the procedure works even better. So these fields look really identical. Okay, there is basically only one way to get a model of an event of that size or larger. In 2019, and this, unfortunately, the two are not much studied. It's a big, nice research line. The impact is enormous. We study much more. Of course, it's our bias, other events that happen in other parts of the world. Remember, science is not an equal enterprise. There are different interests. And we have to be aware of this if you want to think about our global futures, right? So now, if you take the 2019 cold spell in North America, it's, people have studied it in and out. It's the polar vortex, the breakdown of the polar vortex is responsible. This is a much studied mechanism. And these are the features, the global features of the temperature anomaly over a month, basically, in that you see there is this blue spot centered literally on the city of Calgary in Canada, and you see this pattern of large-scale wave. Now, you do this with the model, and you get exactly, literally an identical pattern on a very, very large scale. So somehow, again, you are capturing this typicality. Note that our model doesn't know anything about days. It does not take data from observation, but somehow identify the special pattern, the only pattern that can lead to such an intense event. Again, the constraint is one grid point. Okay, so I put one constraint over the whole model, and automatically I end up in the right and small region of phase space. And if you look at the global scale, again, you find extremely good agreement almost on the global across the whole northern hemisphere. Now, a more difficult and more interesting, even more interesting phenomenon is the 2021 heat wave. That's to me was a huge motivation, because I was just shocked to see the images, and I think this has changed our perception of climate change. Like the 2003 event in France has made extreme events a thing in climate. Before, it was not so interesting. But, suddenly this became very real, because it was one of the most advanced countries in the world, having 50,000 people dying in Paris. I mean, this was a shock. And now, I think this event with the record breaking of 20 degrees in Canada, and, basically the bears surfing, like the Beach Boys, but in the Western North Pacific, was a shock to see. The images were impressive. The glaciers basically coming down the rivers. I don't know if you remember. Now, this event has an important complication, is that the blocking this event is on the Rocky Mountains. It's well known from dynamical meteorology of the 80s already that blockings are catalyzed by orography. So this is a sort of a beautiful example of the interaction between dynamics and then the statistics of heat waves. So we repeated the same analysis, but we wanted to add another level, the level of what is the role of the spatial pattern, and in particular of the heterogeneity of the boundary conditions. So we took the same model run as before, and we selected these 25 grid boxes that follow the Rockies. It's a huge region, as you can see. Now, if you plot in this map the location of the 2021 West North American heat wave, it's here. So this is the core. Okay. Now, I take now my model, and I select, I have a return time for the anomaly in each of these locations. I have a number from the record, from the observational record, and then I construct, using my model, all the averages of the events that at that location have the right anomaly, the same anomaly as in the observation. So it's a conditional averaging based on each location. So I get 25 maps, which you see next. And unsurprisingly, what you get is that if let's focus on these 6 core points. So unsurprisingly, I'm imposing in each of these points very strong heat waves. So of course I get strong heat waves. But the thing I get is that these heat waves are actually the same. So that means there is coherence in the heat waves occurring in this location. So the heat waves of each of these guys, which are even 2,000 kilometers apart, are actually the same event. So there is a coherence. And now I want to counterproof things. So now I take instead intense heat waves centered in each location. And what I discover is that in each other location, I can get strong heat waves, but they're totally different. So the region of the observed heat wave is actually a region of coherence in the dynamics. So once I hit a heat wave in one of these 6 grid points, everywhere you're going to have a heat wave. Instead, if I get the heat wave here, just a few hundred kilometers next, it's a different thing. It's another dynamical configuration. Why? Because basically I am on the wrong side of the Rocky Mountains. That's it. So it's not the geographical difference that matters only, but it's the dynamical connection. So it's like a network here. I found the network structure. Okay. And the key element that I want to convey here is that these are not freak events. They are not a strange, crazy manifestation It's not black swans, are not what are called dragon kings, are not gray. I mean, let's put aside for a moment this terminology. They are part of the natural variability of climate. We can understand and characterize them, but we need to use the right lens. And the right magnifying lens is the magnifying lens that focuses on the tails, not on the bulk. They are not the leftover of the bulk. The tails have their own feature. This is the key, let's say, input of any theory of extreme events. Extreme events are not the leftover of the bulk. They have their own nature that we discover here. And of course, the other thing is that there is, as I said, a special path to get there. So that means that there is the possibility of precursors, to capture precursors. So basically, if the system typically never gets in that special direction, but if it finds the right way to go in phase space, the probability of ending up in these extreme events increases exponentially, basically. So the conditional probability increases. And as a part of this story, seen from the algorithmic viewpoint, is that it is possible to nudge the system, a model, to go in a special region of phase space using the so-called rare event algorithms. With rare event algorithms, I can address this problem from the opposite angle. How can I find, in an exponentially more likely way, trajectory of the system, not forced trajectory, regular trajectory of the system that go exactly where I want them to go? So this is an optimization method that's much used historically comes from statistical mechanics, but now it's been much used to study extreme events in the atmosphere, especially by Fick, Boucher, Dragone, Wouters, and others. And it basically solves algorithmically this problem and shows that there are these special paths. And the special paths, that is the way to find the valley leading you to this unlikely place in phase space, has been confirmed through a totally different approach by Fischer et al. In a paper in 2023, where they approached the study of these 2021 heat waves in a weather forecast sense. And they realized that if they boost the ensemble of initial trajectory in some special direction, the number of events leading, the number of ensemble members going in the right place after the right number of days, so the ability to forecast this very bizarre heat wave increases enormously. So somehow they found, by targeting their initial ensemble, that their weather forecast system could suddenly capture many of these events. Why? Because they were exactly populating the right direction in phase space. So somehow they get the little path that goes up the mountain, okay? Instead of shooting randomly. Okay, the landscape is very heterogeneous. And so this is an amazing paper. I really recommend you to read, because it shows the weather forecast angle of what I described. Now, an element, I will not talk, I mean, there is not something I want to mention that's very important. And this is exactly one of the work that Davide Faranda, my dearest friend and first student, is doing, and I'm part of this, is the study of the attribution of extreme events to climate change. So the idea is, in a nutshell, how does the probability of occurrence of an event of a certain class changes as a result of climate change? And this has to do with comparing the probability of an event of a certain class in absence of anthropogenic forcing versus the probability of its occurrence in the presence of forcing, and studying the relative change in the probability, okay? So this is now done regularly and almost operationally by various centers, and particularly by Climameter, in fact, by David. And you get that not all events that are in the news, that are big events, are necessarily due to climate change, but some definitely are, okay? In the case of the 2021 heat wave, an analysis that I had done separately and before tells you that the probability of occurrence of an event of that class increased by a probability factor of 10, about, or more, or even 100. meaning that a return time of 200, 300 years becomes a return time of 20 years, something that created memories in a sort of historical narrative becomes an event that each generation experiences. So just to give you a sense of this. So now, I don't have much time, but I want to give you a flavor, a dynamical flavor. So far, we have studied the statistics of these heat waves and cold spells. And I try to convince you that there is something special and there is something, let's say, universal about them. But I didn't say much about blockings. So now the dynamic reasons for that. So I will briefly report the work I've done mostly with Andrei Gritzun. So we took a relatively simple model of the mid-latitude atmosphere, a quasi-geostrophic model on the hemisphere. This is the so-called Marshall-Molteni model. It's much studied, used as a toy model of the atmosphere. And this is a model, just to give you an idea, which in the standard configuration we use has 500 degrees of freedom, 37 positive Lyapunov exponents, a Kaplan-Meier dimension of 90. So very turbulent. It has synoptic cyclones. It has very rapid loss of predictability. So it's a sort of a pseudo weather. Okay? So that's the first characterization. And the main thing you see are the usually synoptic cyclones, which are the essence of quasi-geostrophic dynamics. If you measure the fluctuations in the instability, that is the daily values of the finite time Lyapunov exponents and the number of positive Lyapunov exponents on the finite time, you discover something scary. That is, there is a huge fluctuations, this is the most important one, that the number of locally unstable dimensions fluctuate between, say, 25 and 65. So this means that the system has a predictability that is dramatically heterogeneous. Sometimes it's very unstable. Sometimes it's very weakly unstable. And the fluctuation is as big as the mean. This is a nightmare because we would like a system to be chaotic, but always equally chaotic. This creates a lot of problems because it means that the predictability is very state dependent. But does it have to do anything with blocking? And the result is that, yes, this model has a good representation of blockings. This has been much studied. And what you discover is that once you have the onset of blockings, you have a very strong positive anomaly in the instability. So the system sees the onset of blocking as associated with stronger instability, meaning that it requires a special amount of instability to build up these spatial patterns, which are persistent. Okay, this is the first nice characterization of blockings. Blockings are also known from another angle to be associated with regions of low predictability. And that's another separate contribution that Davide and collaborators did a few years back using a dimensional analysis. So blockings, even if they are persistent, they are associated to low predictability and high instability because dynamically, and in fact, in terms of information, it costs a lot to generate them. But can we understand, this could be just a chance. Is there something fundamental about this blocking? And I come now to the very final topic today. So the final topic has to do with the global properties, the global structure, the global embedding of a chaotic system. So when we think about a chaotic system, you think about something going everywhere, strangely, where there is no control. But there is a totally different viewpoint that actually comes from very deep theoretical arguments. Actually, if you have a chaotic system, its attractor is densely populated by unstable periodic orbits. So these are closed trajectories that are unstable by definition that populate the attractor. So what you see as a chaotic motion is, in fact, can be equally well be described as a perpetual repulsion of a trajectory from one unstable orbit to the other. So the system follows closely one unstable orbit, then takes another unstable orbit, then another unstable orbit, and so on. And you can represent a chaotic flow like this. It's a very crazy vision of a chaotic flow. It's against our intuition, but let's keep in mind, our intuition is not necessary a very good one. So you see, yes, so this is Lorentz 63, and this is the closest shadowing UPO. This is a work of my student, former student Chiara Maiocchi. And this angle has been very pushed forward very strongly by Predrag Cvitanovic to study turbulence in fluid flows. Now, for low turbulence, this works perfectly. But does this work? Does this give us information in a highly turbulent flow like ours? And what has this to do with blockings? Because remember, a UPO is a true solution of the nonlinear equations. So it's a true mode of the atmosphere. So I want to show that blockings are associated with a special class of these modes. So they are special dynamical features of the atmosphere. If I do this, I give an ontology to this blocking. This blocking exists as something special. And indeed, we took the same model, we computed and found about 2,600 UPOs, which seems a lot, but of course it's a small number. This is a highly dimensional model. And what we discovered, the most interesting things, is that the UPOs have a number of positive Lyapunov exponents or unstable dimensions, which ranges between 30 and 50. So this is actually a mathematical proof that this system is non-hyperbolic. It's a proof that this system, which seems like a cloud of points, is instead a complex pattern of region of high instability and low instability. And the system enters region of high instability, then goes back to low instability, then back to high instability, following bundles of this trajectory. Very good. So we have a proof of unstable dimension variability, and we have in this room and in this university leading expert in this. So we see this phenomenon in an atmospheric motion, and it's very relevant. Why? Because indeed, I can compute, I can evaluate if any of these UPO is associated with blocking, and I discover that blocking are disproportionately associated with the highly unstable UPOs. So a blocking is what we see in a weather map of a deep object, which is highly atypical, highly unstable, but that we still populate in our dynamics. So the system is usually, let's call it in a red state, and then suddenly enters the blue state. The blue state is blocking, what we see in the map, but it is a highly unstable UPO. So we have a connection between the phenomenology of the weather and the very deep mathematical structure, what is called the skeletal dynamics of a chaotic flow. So now, reaching this, I was very happy because for once, I managed to understand what the blocking is. What I see is not what I get. No, what I see is this strange flow. So it's like a topological mess. And I remember, I was talking to years back about this to David Ruel, one of the true giants of so many things, let's say mathematical physics, dynamical systems, and statistical mechanics. And he said, remember, if you see features in something, there must be something stronger deviation from hyperbolicity in dynamics, because hyperbolic chaos is like a cloud of featureless stuff. Instead, there are features, and these features are associated with the breakdown of hyperbolicity and this unstable dimensional variability. So,
shouldn't those UPOs be relatively more stable?
More unstable.
Stable.
The blocking says more unstable, yes.
But if it's more unstable, you can easily break it.
And
if it's more unstable, you can easily break this.
The thing is that since they are more unstable, they are more rarely visited. In fact, the blocking is a relatively rare phenomenon. Okay? So, since they are more unstable, the trace formula tells you that you're going to spend less time around them. Okay? They count less because the weight is exponential.
But because it's very unstable, so any small thing can just...
Oh, yeah, but what you do is that you stay there for a little bit in a bundle of this trajectory, not in one, and then you are repelled to other, less. Let's say you classify trajectory as very unstable and very stable, and average. So when you are in the unstable, you stay there not so frequently, of course, but a disproportionate amount of these unstable are blockings. So blockings are due to the fact that you rarely visit more unstable UPOs, but once you are there, these are most likely to be blockings.
They last long.
And
they last long.
once you are there, you stay for a while. No, in this model, there is an exponential decay of times. So here you don't. So the problem is that the long persist. In general, you tend to have, so the lifetime of the blocking in a simple model like this should be exponential. In the real world, it's not exponential because then you have memory effects due to basically water vapor. So water vapor makes things dramatically more complicated.
Yeah, so do you have any data supporting that blocking are more unstable?
Yes, here they are. Yes.
How do I see this from those figures?
Yes, because this is the distribution as an example of the number of unstable directions.
Okay.
And if I do the distribution, let's say conditional on the fact that this is a blocked, because some of these UPOs are always blocked states. You see that as an example for the Atlantic blockings larger than 3 days, it is the mean, it's much larger. If I take global blockings, that is both Atlantic and Pacific blockings, are only few events, are rare. These are very rare. The mean of instability is almost in the tail of the average. So the more, if I move on this side, a disproportionate amount of UPOs are associated with blocking. Okay.
So that's the number of unstable directions.
Yes, and then you get the same for the first Lyapunov exponent and the sum of the positive one. So you basically have this sort of fractional, it's like they say if you conditional your statistics on the occurrence of blocking, you always choose very highly unstable UPO, which are then rarely visited, of course. That's why blockings are not so common. So it's self-consistent on this.
Oh, very interesting.
Yeah.
Yeah.
And the bonus, an important thing, and I will stop here now. There is other things I'm happy to talk about in the questions, and the other methods to do this classification. I think I've said sufficient number of things. Is that we know that if I have unstable, let's say variability in the number of unstable direction, I lose a very important problem in modeling. That is the shadowing property. So if I have a good numerical model, it will shadow for a very long time the true trajectory. If I have this pathology, shadowing is lost. That's why I believe representing these features is an extremely difficult task. It's not a problem of the technology of the model. It's a problem of the essence, mathematical features behind it. So this is very fascinating. This is a very complex tool. And one of the side effects is that it makes data it's one of the barrier to data assimilation, because many methods of data assimilation are based, as an example, on assimilating only in the unstable subspace. That is, controlling the system only on the unstable tangent manifold. But if I can always define an average number of unstable dimensions, using the number of positive Lyapunov exponents. But if locally I have region where the error grows in many more dimensions and that I don't control the error in this extra dimension, I will fail in my data simulation. So this has very important implications in merging data and models. So that's something I found very fascinating as well. Okay, I will. There are a few other aspects that I will not talk about because we don't have enough. I think it's already material and more than enough material. So I think I try to convince you first that if we want to improve our ability to understand, predict, make a sense, project, in fact, in the future, persistent extreme events in the atmosphere, we need to ground this into very solid mathematical and physical tools. These tools exist, so we can benefit from a huge and beautiful piece of literature. With the current data-driven methods, we can improve on the classical results. Building on the theory and improving algorithmically, having an efficient method to do this. All I've shown you algorithmically is quite primitive and on purpose. So I was interested in making just a case that this is possible rather than solving the problem. But I am sure it's possible to do this very well, much better than I did. The indication is that if things work in such a primitive way, if I use advanced methods, it will work for good, and it works already. The last thing is, we can also substantiate the existence of modes of the atmosphere that are associated with heat waves and blockings through methods that are used in other areas of complex system science, in particular Markov state modeling. This is a huge set of techniques to study complex systems based on Markov chains and hidden Markov chains. So we have used that, and you find again the same states. So there is something fundamental there, again, to be explored. Okay, thank you very much.
Thanks very much, Valerio. That was excellent. Looks like we have questions to start. So,
well, thank you, Valerio. I think, you give me some homework problems to do. In a sense that, my group has developed some machine learning models in the past few years to predict chaotic systems, with some success. But somehow dynamic system with unstable dimensional variability, we didn't study. I don't know why. And now we're going to study.
I think it,
So it's so important here. So yeah, I learned a lot from.
Yes, and we can use as an example, if we want to use this model, this Marshall-Molteni model. This is really a sort of a fundamental, simple, but not really simple model of the atmosphere. So people use, as an example, is the sandbox for all data simulation methods, for all testing. So if one understands how this model works, and as an example, to study the impact of orography, the impact of anomalies, so symmetry breaking process. This is a fantastic numerical lab, and I think honestly, this result on this variability in the number of a stable direction is a big open question that needs to be understood.
Yeah, I did unstable dimensional variability many years ago.
I know, I know very well, and that's how
I forgot that there's such a thing until today.
and that's how I got to know you, actually.
Yeah, it's very important. We're going to study it. I'm going to ask some students to look into it. Yeah.
Okay.
Other questions? There's no bad question, remember?
No.
So.
Yes.
I have a bad question.
Okay.
Could you apply this analysis to hurricane prediction?
Okay. Hurricanes prediction. So surely, these trying to understand. You mean predicting what? The paths, the intensity, or?
I was actually thinking. Oh, I don't like this. I was actually thinking at the very early stage of hurricane, can you now get a sense of whether it's likely to turn into?
Yes.
You estimate the Lyapunov exponent.
I think that what you can do, surely using these rare event algorithms, you can try to identify what are the most likely outcome with an exponential accuracy with respect to using regular Monte Carlo. So that's the idea. So I think you have the flexibility of asking questions like how likely is to get, because what you do basically is that you target, you have your initial conditions, state of the climate on this day, and then you want to ask yourself how likely is to get, this, characteristic squared wind velocity in this region, and then you basically nudge things. You sort of use a score function, and you try to selectively choose bits of the run that go into the right direction, and you cut the simulations that don't work. So you basically repeatedly do the twins experiments and cut all the wrong branches. By counting how this works, you estimate, and you basically estimate by how much you have increased the probability of this event through your algorithm. So how much you have cherry picked. So you cherry pick, but you know how much you cherry picked. Then you invert it and you say what is the probability. And this is how you estimate the return time. And this is what Boucher, Ragon, and company have been doing, and this works very well. It works exactly because what you are doing is following the sort of optimal path, which is what I discussed today. Yes, that's why.
That's what I was thinking of.
Yeah, that's so.
Finding the path through the valley.
Yes, and it can be a very counterintuitive path, as an example. Yeah.
Next one.
Yes.
Hi, thank you for the great presentation. I'm a PhD student, and you told about a little bit on the last data-driven methods could be useful.
Yes.
My understanding of the data-driven models is that there has to be a lot of events so that the models could actually learn from those. But given that these events are such rare events, do you see there's an opportunity to use machine learning data-driven models to unfold something?
So I tell you this is, so now you have basically what you can do is to extract, basically you want to take advantage of the power of statistical mechanics, and in particular what is nowadays seen as the framework behind statistical mechanics, which are basically Markov chains. Okay, so Markov chains, if you take them to the limit, you get whatever you want. The problem is that you can't always do that. So the idea is you have assume you have a system living in a high dimensional space. And you can pre-process and reduce the dimensionality, or you can also decide not to do that. Now, the protocol is this you can use. You construct at the beginning with k-means a Voronoi tessellation of the space. And so then you put events in these boxes that are defined by the Voronoi tessellation. Then you construct the stochastic transition matrix following your trajectory. And now you have your fundamentally right statistical model. So you don't need to know the equation. These are the equation in the projected space. So you don't have to make assumptions. That's the real world. So the world knows this. The equations are our way to see the world. Once you do that, you have a Markov chain. When you have a Markov chain, you have a horde of theorems, and you can, example, study the eigenvalues and eigenvectors, and then you extract everything. So the correlation, the modes, and so on. So that's something we did without doing anything very fancy, on the ERA 40 data in the mid latitudes. And as an example, you discover a lot of interesting things. You discover, as an example, that there is no time scale separation in the atmosphere. So you can't really separate modes, which we know, it's my second slide. But now you see it in a dynamical setting. So you can understand why it's hard to do weather prediction in some sense. And then, by looking at these modes, as an example, you can identify this special, like you can identify special patterns associated with these modes that indeed now look like a zonal flow and blocked state, and this blocked state will be associated with certain anomalies of temperature. So basically, you distill the dynamics in a non-human way, if you want. It's not the way you look at data. It's not the way you would look at data using equations. You let the data talk by themselves, and you add no bias. That's very important. It's not your choice. The data will tell you what are the modes. And we were very surprised to see that, as an example, we look at the Atlantic sector. We found the mode in this method, so without knowing. And then we applied the evaluation, the indices, telling you whether this state is blocked or not. And this state had 100% of block state, and this other state had 0%. So the system had found the fundamental dichotomy between these two states without knowing what a block state is. So this means that our intuition of a block state developed over 70 years of meteorology is not just our insanity or our illusion. Oh, and of course so. I would never think it is. But somehow the data finds this object. Of course, an alien civilization would not call it blocked state, but will find it. So that's quite surprising. And these are then conducive to special patterns of, as an example, temperature and precipitation. We have a lot of these results. So they emerge somehow. So this is very encouraging. We have only done some on this, not enough. So now there's been a recent paper by Anachi and others where they go from Markov chain to hidden Markov chain, so finding the deeper level. But the result is essentially the same. They find, their work is better than ours because they go deeper, but they find these emerging patterns. So that's, I think, very encouraging to provide some systematics in the context of weather and climate. The problem of weather and climate is that a lot of research is implicitly based on very subjective angle, which is a beautiful thing, but it's also a limit to intercompare results. So here we have this new science that allows us to, let's say, evaluate this and find again some new results. So one can say, oh, there is nothing new. No, there is everything new, because we rediscover things in an objective way. Okay?
Thank you.
You're right.
Carol, I have a question.
Thanks.
Give me
Presentation. All right. Okay, so my hometown is Cagliari,
Yes.
just similar to Calgary.
Yeah.
What if you change the point
Yes.
from Calgary to Cagliari? So how does it? This
Yeah.
comes from a civil engineer that doesn't have this type of background. So
But this is
block depends on the
you go from Cagliari to Cagliari.
in Sardinia,
Vice-versa.
Italy, right?
This is a really nice line, to start a paper, and I might steal it in the future.
Okay.
Now, what happens is that in this case we were targeting just out of our, let's say this is part of the sort of heuristic thing. So I'm not advocating for a totally top-down approach. No, I'm advocating to both approaches. So here the thing is, historically, there's been an important event, which was this heat wave. So I want to study this heat wave. And I have a methodology to reconstruct the atmospheric condition leading to this. Now, if I want to study a heat wave that, Western Mediterranean, I can repeat exactly the same protocol, and I will find a different typicality. Now, what is interesting is that, I didn't mention, is that if I look at a heat wave in Moscow and a heat wave in Nizhny Novgorod, which are about 300 kilometers away, it will be exactly the same pattern. Why? Because this object has an enormous spatial correlation. But sometimes, if you cross some visible or invisible boundaries, not the nation boundaries, we are all together in this business, you shift to different regions, and then suddenly there is a discontinuity in the class of events. So it's not the same, moving, the sensitivity can be enormous, as I showed you in the other case. So now in some places, like the Mediterranean basin, where you have orography, strong orography, you have, of course, the sea itself, you have, more temperate climate on one side, desert on the other. Small changes might dramatically change the way a heat wave happens. Now, if you are as an example, someone working for the European Union, you would like to understand better what is the region of coherence of heat waves in different parts. Because, of course, if you have a heat wave hitting France, and you know that these heat waves are usually associated with heat waves in Germany, and not to heat waves in Spain, you need to prepare differently. Okay, even if the distance is the same, okay, more or less. So the same is, so it gives you a spatial coherence, which I think it's incredibly important to evaluate risk. So one could extensively repeat what I've done. It's very easy to do. You just need a long climate run, and you can fix some targets. And as an example, check, are the heat waves in Arizona linked more closely to heat waves in Texas or to the heat waves in California or in Nevada or wherever? And the result might not be what your intuition tells you. But in terms of preparedness, it's very different because, again, these are systemic risks, because look at the spatial scale multiplied times the temporal scales, and you realize what can happen. And by the way, there are also global teleconnections sometimes here, but even forgetting the global teleconnection, still in one region, extended region, you have a very different, you have heterogeneity or homogeneity on different spatial scales. This is very important as an example, to manage water resources, to manage the logistics of an intervention against wildfires or so on.
Yeah.
Thank you.
I have another one if I can.
Yeah.
Okay. So, still in the same,
Yes.
same idea. So you had the portfolio of 20 pseudo.
Yeah, yeah, very good. Yeah.
Okay, so before that, you had everything that led to that, to those, so you could extract from the model all the trajectory that led to that.
Yes.
So you can develop a climatology of the trajectory. Is that complete noise?
I have not done it, but my bet is no. We have not done the paths. These are only the averages over the period. So what you propose is the exact to do. So you have, this is exactly what statistical mechanics will tell us. It will tell us that the convergence is not on the paths, on the average, is on the paths. So if it's on the paths, it's also on the average. So I'm looking at a weaker condition here. So it's the clustering over the averages. But what will happen is that the paths are similar.
So it's predictable.
That's why, of course, that's the thing. That's the magic of, this is another seminar, the seminar on noise-induced transitions in metastable system. So how you get n-tipping in climate is that, and this is all the magic of large deviation law. It tells you the most likely among the unlikely events. So conditional on the occurrence, you have a deterministic law. This is the instantonic trajectory. Which is, so if you observe this, then this has gone through this path. An example on the path is, if I tell you, I've hiked up a small hill, I give you no information about my path. If I tell you I hiked above 2,000 meters high mountain, there can be 10 different trails going up. But if I tell you I've been up to the Everest, there is one path. So conditional on you having been on the Everest, I know exactly your path with probability 1 in that case. Yeah. Of course, if you invent the second path, you enter the history of alpinism. You have broken large deviation law, okay? And you can think this is, how roads are done, If you want a road, is the large deviation solution that the society has found for this path. Sometimes there are many roads, but not always. If you have a mountain pass, you have only one road, not by chance. Yeah.
Thank you.
Yeah.
Any others? Okay, I'll do the bad thing of asking you one last question.
Yeah, go ahead.
So my work's been much more focused on the medium range problem.
Yeah.
And I got away from the climate change one because I did not see the value in it, to be honest. But one of the things we have done over the last 25 years, which resonated very closely with what you're talking about, is looking at the dynamic meteorology through the lens of a hidden Markov model over and over again. The difference is that in most cases, we also considered a conditioning variable, which was typically some form of SSTs or whether or not there was prior snow cover and things like that. The probabilities of the states depend very strongly on those boundary conditions.
Yes.
And in the hidden Markov model in particular, we also looked at the persistence state probability as a surrogate for the Lyapunov exponent.
Okay.
And computed that. And of course, it's the global versus local challenge.
Yes.
So the deficiency of the hidden Markov model is you end up with domain dependence. If I change the domain, I don't get the same results. The second is that it's global rather than local, unless you condition it on something dynamically that is forcing it. So now what I've been wondering, and I would love to get your thoughts on, is that if I look at, there's one other problem, which is the question that, Giuseppe asked in a way. So in a hidden Markov model, it's the state, the atmospheric state at that geographical location that it will cluster. Whereas if I look at a attention-based transformer model, it is tokenizing that phenomena so that it is no longer restricted to a particular geographical location. Okay. So that's the basis of my question is now that we are working with those models, have you thought about how you take the latent state of those models and connect it to these dynamics?
So, in what we have done here, you have, it's the tessellation, and then the construction of the Markov chain is not due to local properties, in the sense that we are in a high dimensional space. So let me find, so this is the classic approach, really informative by Wotar, Gill, Kimoto, of studying a transition between weather patterns through Markov chain. So now the Markov state modeling creates another level, so constructs the states ex post, not, you don't choose the state and then study. So now the thing is, as an example, in our case, we notice that, again, this is not a silver bullet. Things work, so we have a sufficient amount of data to do this game if we limit ourselves to a sector, not a small sector. So we did 60 degrees up to 120 degrees with the 50 years of data. But if we had 1,000 years of data, we could do the whole world. So these are global states. Now, the cool thing is that these global states, this was, as an example, a nice, so we cluster, we look at information here, but then when we plot globally. So what you find is that even looking at a relatively limited regional space, you discover global patterns. So I remember when I started this work with Laio, Alessandro Laio is really one of the lead experts in this, on the basically chemical physics, biological physics side of things. He's one of the inventors of these methods. And we plotted it. He said, why are you plotting outside the region of interest? Because that's our goal, The rest is noise for me. I said, no, the rest is the game of the atmosphere as teleconnection, whether we like it or not. And in fact, what happens is that these, as an example, let's look at this case. So in this case, we look at only this region, but the patterns, and this is not even the most striking one, very strong pattern exists on the other side of the world. Of course, if I change my, as an example here, we did an analysis on the Atlantic sector. I think I had a slide, or anyway, it's in the paper, on the Pacific sector. Okay? And as an example, one mode that we detect looking at the Pacific sector is the global blocking. So somehow the system finds, only looking at the Pacific, but then you plot everywhere. So this information is not in the selection of the model, you discover the global blocking. So somehow another way to see it is, even looking locally, you might extract global information. So this is again encouraging, because this is not information that has been fed into your model. And if you look at the larger sectors, you find the NAO, you find the global teleconnections as an example. So again, of course, if I went to a latent state, I will probably clean up better these things. But I already think this is, as I said, is the first step. But I think there is a lot of scope. And of course, again, this was just done on observations. What I think would be nice to do is that now take three, make some of the friends who run the climate models, for the sake of it, very happy. We take few thousand years old runs for 2 or 3 climate model. You repeat this analysis with exactly the same parameter, and you're able to say if these models are seeing the same systems or not.
They don't.
But no. But the problem is that if they don't, if they do, you say, okay, these models, despite their differences, are at a coarse grain level in a very rigorous way. So this is things where you can write theorems in principle are doing the same thing. If not, you can say these guys look similar, but they are heterogeneous objects. And as an example, you should never, under any circumstance, and no circumstances, do ensemble averaging, mixing them, which is instead the common practice. So it tells you, maybe I don't know if model A is better than model B, but they are heterogeneous. So don't put the data together, because the only result is to get rid of any potential information you have there. So that is, I think, important. Yeah.
Well, let's thank Valerio. We can liberate people to go and eat and have more